we're going to look at heterogeneous equilibria. So we have more than one phase in this situation. The position of a heterogeneous equilibrium does not depend on the amount of pure solids or liquids. The solids and liquids do not show up in the K expression. So for example, we're given the decomposition of water. Water is a liquid. It decomposes to hydrogen gas and oxygen gas. So if we need to show the Kc, that would be the hydrogen concentration squared times the oxygen concentration. But because the water is liquid, it does not show up in the K expression. If you're asked to draw a Kp, show a Kp, that would be the partial pressure of the hydrogen gas squared times the partial pressure of the oxygen gas. So let's do an example. The Mond process for purifying nickel involves the formation of nickel tetracarbonyl gas. A carbonyl is a carbon oxygen from nickel metal and carbon monoxide gas. We're asked to write the equilibrium expression Kp. So first we have to be able to write the balanced equation. Nickel is a solid, carbon monoxide is a gas, and then we get our product, which we were told is a gas. Then we're asked to write the Kp. So our products are on top. We only have one product. Our reactant is on the bottom. And then notice that nickel is a solid and it does not show up in the expression. So you're going to want to absolutely remember this, because the entire semester, do not use solids or liquids in the K expression. Multiple equilibria. That would be when you have a sum of reactions. If a given chemical equation can be obtained by taking the sum of other equations, the equilibrium constant for the given equation equals the product of the equilibrium constants of the other equations. So for example, we have this first reaction, carbon monoxide gas plus hydrogen gas in equilibrium with methane and steam. And this has a K1 of 3.92. We have a second equation, methane plus hydrogen sulfide gas in equilibrium with carbon sulfide gas and hydrogen gas. This reaction has a K2 of 3.3 times 10 to the 4. So what we're going to do is we are going to add up these equations. So when we do that, the carbon monoxide stays. This methane is going to cancel with that methane. The hydrogen sulfide stays, we have that. This carbon sulfide stays. The water stays. And then notice that all three of these hydrogens cancel with three of these. So we do have one hydrogen left. So when we take these equations and add them up, this is the reaction that we will get. So we said that when you have the sum of the equations, the way to get the KEQ for the ultimate reaction here is to multiply the individual K's for each one of these. So that's why our new KEQ is a multiplication of our individual KEQs, and that gives us the KEQ for our overall reaction. Okay, this is an important concept coming up. This is called reaction quotient. So notice that the reaction quotient uses the letter Q. So Q is an expression that has the same form as the equilibrium constant expression. However, the concentration values are not necessarily those at equilibrium. So this is what you're going to want to know and memorize. If the Q is greater than the KEQ, the reaction will go to the left. If the Q equals the KEQ, the reaction is at equilibrium. If the Q is less than K, the reaction must shift to the right. So let's do an example. We're given a gaseous mixture. It has the following composition. We're given the molarities. And we're asked where the equilibrium lies. So this is the catalytic methanation process, and we had already set up that expression before. This is the KEQ for that process. That was earlier in the notes. So it's methane, water on top, and then carbon monoxide, hydrogen gas on the bottom. So all we do is we plug the values in that we were given, and we solve for the Q. We get a 6.25. Now, in the previous problem, we had been given the KEQ. So we compare this Q to the KEQ that we were given in the previous problem. And in this case, the Q is larger than the K, so the reaction will shift to the left, and therefore the equilibrium lies to the left. Okay, we'll do the other problem next time.